Hello everyone, welcome to 𝐿ustraca. In this lecture, we are going to discuss about a very important, you can say, topic, which is very simple also. But many of the young engineers like me, who are recently using STAAD.Pro for concrete design, or who are using STAAD.Pro for a long time, but they are not that much familiar with the calculation part of STAAD.Pro. So many have this particular doubt. Then when we are designing RCC column in STAAD.Pro as per IS 456 criteria or IS 13920 criteria, we see that many of the times when the reinforcement requirement is less than the minimum minimum percentage. So as per code, it should assign some minimum percentage of reinforcement, but we are seeing that STAAD.Pro is assigning the reinforcement percentage less than the minimum percentage required as prescribed in code. So what we will do, so this is kind of a I can say ambiguity. We are thinking whether it is STAAD is doing it wrong or what we have to do. So this problem or this issue we will discuss. We will see what is the fact actually, whether we are aware about the whole story about behind it. So this is what our you can say topic of discussion for today's lecture. Okay, so here to demonstrate this, I have created one very small example structure. I have created the structure with some you can say fundamental properties, section properties for beam and column, and I have given fixed support and loading. If you see, only two load cases I have created: dead load with self weight and 12 kN per meter uniformly distributed load on the beams, and the floor load of 2 kN per meter square, which is dead load. Okay, and in live load I have taken a floor load of 2 kN per meter square in all the floors. Then I have created one load combination, which is 1.5 dead load plus 1.5 live load. Okay, so this is my loading, and I have given the analysis command, and also I have defined the concrete design command for the column design. So if you see here, I have assigned this column design parameters as for IS 456 code. So if you want to know about the column design parameters and how the software is performing the design, what is the significance of these parameters, I have a detailed course on RCC building design in STAAD.Pro. So you can check that out in the link for my Android and iOS app. You will find in the description of this video. So you can just download the app and you can find the course there. You can check the syllabus and also the different open items, or you can say free contents, which will give you a overview about the course. So this kind of detailed discussions are actually made there, and it's still going on. So we'll be uploading many more such detailed contents. Okay, so you can check that whenever you are free, if it is you can say, if you find it interesting. Now I have assigned these parameters. So what I will do now, I have already given the command also for start concrete design and ending the concrete design, right? So I will just run the analysis. It will run the analysis. So you can see the analysis is completed. So I will just click on this view output file and I will click on done. So here the output file is open, and directly I will jump into the column design. You can see the first one is column 5. The section length of this column, the node to node length, which is 3 meter, 3000 mm. Cross section is 300 mm by 300 mm. Okay, and cover, the clear cover we have assigned, which is 40 mm. Fine. Then now the design will be started. So it is an unbraced column, long column. So as per the I can say ratio for long column and short column, it is found that it's a long column. And if you see here, the design is performed in different cases. So what I have given a command that the software should check the minimum eccentricity criteria one axis at a time as per the codal provision. Okay, so in that case it will create different cases for y-axis first. So you can see here the minimum eccentricity moment is calculated for y-axis first. Okay, and obviously the slenderness moments are also added here, and this is the final moment for which you will be designing. The moment is very less, so in that case you can see it is load case 3, which is my combination actually. So the moment is very less, so you can imagine that for the 300 by 300 section this moment is very less. So in that case the minimum percentage of reinforcement as per the prescription of code we need to provide. Correct. I will show you the codal provision also for that. Interaction ratio also you can see it is 0.61. so this interaction ratio is as per the provided you can say required steel. Okay, so the required steel is 156.36 square mm. We will check whether it is the minimum percentage or not. Okay, same thing if you see about z axis, and it is done. Okay, and if you see here another joint at joint 4 also it is done. Okay, at joint 4 also it is done, and here you can see the PU is 208.38, and in this joint also in both axes it will be done, Z and Y. Correct. So now if you see the nodes 1 and 4, so basically this is my beam number 5 or column 5, and we have node 4 and 1, right? So first it will check the capacity, or you can say requirement, at this node 1. So in that case obviously the load of this column and this column will be coming on this node, right? Or when it is checking at node number 4, the load of only the column above it will be coming on this node number 4. So automatically you can see at when the design check is done for node number 4, just let me show you here. Yes, it is load case joint 1 and joint 4. So you can see the axial load 208.38 is less than the axial load above, which is 217.93. Okay, so this is the general case. You can easily understand when you see. Now our concern is the result that we are getting. Okay, so finally if you see the required steel, it is given, which is 149.51 square mm. Correct. Required steel area. So sorry, this is for this condition. If I see critical condition, so for critical condition among the all 4 cases, the required steel is 156.36 square mm. Okay, so if you see here, even if it is written that when we provide, so this is the required steel and the provided steel is 412 dia, and if you see here clearly it is written that the provided steel percentage is 0.5% only. Correct. So now the problem is, if I go to the code, the IS 456 26.5.3.1, it says the point A, it says the cross-sectional area of longitudinal reinforcement shall not be less than 0.8% and nor more than 6% of the gross cross-sectional area of the column. Okay, so if I just show you here that first we have already seen that it is not 0.8%, it is less than 0.8%, the provided one. Even if you see the steel required, this is also, if I just keep this aside. Okay, so the required steel, if you see 156.36 square mm divided by 300 multiplied by 300 multiplied by 100. So the required steel percentage it is given, it is also only 0.1%. Okay, of gross cross-sectional area, and provided is 0.5% of gross cross-sectional area. So now why STAAD is actually doing it? Okay, whether it is doing it wrong. So now let's come to the next part. So till now whatever you have seen, this is just one part of the story. Most of the time this is our, you can say, intention that, or you can say this is our human behavior, that we only see one part of the story and we start you can say making comments on that particular thing only. Okay, we do not try to, most of the time we do not try to discover more, to know more. So though many of us know it, many of the engineers who are practicing, they know it, but those who do not know, those still have this doubt, let's clear it today. So now the same clause, if I go to the point B, okay, so here if you read it, it says that in any column that has a larger cross-sectional area than that required, okay, then that required to support the load the minimum percentage of steel shall be based upon the area of concrete required to resist direct stress and not upon the actual area. So it says that when you have a larger cross-sectional area, so that minimum percentage of reinforcement, it will not be on the minimum percentage of gross cross-sectional area, but the minimum percentage of required area to resist direct stress. Okay, so direct stress means the axial load, the stress which is coming due to the axial load. Okay, it is not bending stress, it's direct stress. So let us now understand what STAAD is doing actually. So if I again see it, this particular thing, let me just keep the calculator here. You can see there is one more thing which is written, which is the required concrete area. So what is this required concrete area? We have already given concrete area 300 by 300. Why STAAD is calculating this required concrete area? If you see here, so as the code says 26.5.1 point B, that the required concrete area will be the required area for resisting direct stress. So we have already seen what is the maximum I can say PU, axial load. So if you see here, the maximum axial load on this column, it is 217.93. Okay, so if you remember that what is the maximum I can say stress that concrete can take. So the limit of stress, we know it is 0.446 FCK, correct? Here our FCK equal to, we have considered 25 MPa FCK, grade of concrete, correct? So now if I want to find out the direct stress, so it will be equal to PU by if I want to let me just write it in a different way. Actually we are finding the area, right? So we know that PU by area is equal to stress. So if I consider this stress as my maximum stress due to the maximum axial load, so maximum stress that concrete can take, it is the 0.446 FCK, correct? So what I will do, I will just write it, maximum compressive stress, remember, so it is 0.446 FCK. Okay, so this is actually maximum compressive stress on concrete, the concrete can take, correct? So now to find out area, what I will do, I will take A equal to PU by 0.446 FCK. So this is the area required to, you can say, to support the direct stress, correct? The maximum direct stress. So here in our case, if I just see the maximum load that we are getting, it is 217.93. so area required equal to, as I have written, PU by 0.446 FCK. So I will just put it 217.93. so it is in kilonewton. I will convert it to Newton, 10 cube divided by 0.446 multiplied by FCK is 25. Okay, so if I just do this here, so it is 217.93 multiplied by 10 cube divided by 0.446 multiplied by FCK. So you can see here the result we are getting 195.19545.29. Okay, so if I just take you, I'll just write it here, it is 19545.29 mm square, correct? So if I just take you to the final result of STAAD, you can see here Yes, so you can see here we are getting 19544.96, a bit, let me see, 217.93 only we have written, right? Okay, correct. So yes, so the required area, it is written 19544.96, a bit difference, but it is almost the same. 199.45.96 means 199.45.45, you can also write it here, right? So actually code what is doing, it is finding out the required concrete, okay, concrete area based upon the maximum axial load by the you can say maximum compressive stress that the concrete can take. So this is my required concrete area. Now what it will do, it will find out the minimum percentage required for that particular column based on this particular concrete area as per the code. Code says that you need to find out the minimum percentage based on the required area to resist direct stress and not upon the actual area. Okay, so this area it is found. Now if you multiply 0.8%, so if I do let us consider this only, 19544.96 multiplied by you can say 0.8%, so 0.8%, you can see here we are getting exactly 156.36. so it is the minimum percentage required, 156.36 square. Okay, so this is nothing but the if I just show you this is nothing but the 0.8% of this value, which is this, which is nothing but, I will write it here, required area to resist direct stress. Correct? So this is my minimum percentage required. Now what you will do, general column design calculation, you will you can say find out the moment capacity, and I can say based on that what is the percentage of reinforcement required. So you can find it. If that percentage of reinforcement is less than this minimum required, so this minimum required percentage will be assigned. Or if the as per the design for the moment and you can say biaxial moment, if it is percentage of reinforcement is more, so that particular moment you can say reinforcement will be assigned. In this case the minimum percentage reinforcement is governing. Now in the column which is 300 by 300, obviously at least 4 number of bars we need to provide, and this distance cannot be more than 300 mm also, right? Because when you are providing stirrup, the you can say the transverse legs of the stirrup cannot be greater than, the spacing between the legs cannot be greater than 300 mm. So we need to provide the reinforcement also in such way. Correct? So here at least 4 bars we need to provide. So 4 bars of 12 dia provided, and the percentage of reinforcement it is showing actually 0.5%. so here when it is showing the percentage of reinforcement, it is actually showing a percentage of reinforcement based on the gross cross sectional area. Okay, so if I just show you that the what is the yes, so what is the reinforcement area if I provide 12 number of 4 bars of 12 number 12 dia, so it is 452.39. it is the reinforcement area divided by, if I multiply 300 divided by 300 and multiplied by 100%, so you can see it is 0.05, so it is 0.5%, correct? But if I multiply it with the required you can say area of concrete, so which is 19544.96 as calculated in software, so you can see it is only 2.3%. so it is much more than 0.8% of the gross cross sectional area, much more than 0.8% of the required cross sectional area which is we have provided. Okay, so actually STAAD, what percentage is it is giving, it is not on the gross cross sectional area but on the required cross sectional area to support the direct stress as per IS 456 26.5.1 clause point B. Okay, so don't be confused that STAAD is doing it wrong. Actually STAAD is doing it correct as per the codal provision. Okay, STAAD is doing it correct as per the codal provision. So I hope it is clear how STAAD is finding the minimum percentage of you can say minimum area of reinforcement required. Now if you see here in most of the cases, here also the required percentage of reinforcement is less than this, and the other cases also the required percentage is exactly the 156.36. That means this moment, the percentage of reinforcement required to support this biaxial moment, the axial load and the two axis moment, it is much lesser than for which we need to provide the reinforcement. It is much lesser than the minimum reinforcement required. Okay, so that's why this is the governance criteria, and this is how STAAD has provided the reinforcement in you can say column, RCC column. Okay, so rather believing the only one part of the story, if we just look into the second part, if we just try to discover more, there are actually facts which we can find out, and this is how you can say we have tried to clear your doubt. So those who are already known to this particular concept, so obviously most of us, those who are practicing for years, they obviously will be knowing it, but those who are new to STAAD Pro or those who have not, you can say, checked this particular clause, so they might be having some doubt regarding this. I hope this particular lecture or this particular video will be clearing your doubt totally. Okay, so still if you have any doubt regarding this or any other topic, you can always write me in the comment. I will try to solve your doubt as early as possible as per my understanding or as per my knowledge. Thank you and see you in the next lecture.